So I gave you a batch of 14 quadratic trinomials. Every one of them was a polynomial with 3 terms in it, and the degree of each of these polynomials was 2. Right? They all started with an x squared of some kind, and then had a middle term with an x to the first power, and they had a constant. And the question was, if you were to factor these polynomials, then which of the factors up here from this list are actually a factor of the polynomials that are here? So for example, if we look at this one, x squared minus 2x minus 35, how did you figure out what the factors were for this particular polynomial? What was your decision process? So the decision process here is to take a look at the constant term, which in this case is negative 35, and ask what pair of numbers multiplies together to give me negative 35, and also adds together to give me negative 2. And so you decided that negative 7 and positive 5 was the pair that works. And so then looking up in your list of factors, you found out that it has a factor of x plus 5, so we'll write it in a D, and it has a factor of x minus 7, so we'll write it in an E also. Right? And that very same decision process works in almost every one of the examples that's up here. There's 2 examples where that process by itself isn't enough. For those 2 examples, there's a step that comes before trying to use the sum and the product game. So I'm going to call that the second step. What we're ultimately trying to do here is build an overall strategy for how to factor things that look like trinomial polynomial expressions. Play the sum and the product game, which worked in all of these cases here, and I would argue actually doesn't work in the 2 cases that I gave you on the bottom row. And so those are actually going to be the jumping off point for the next part of our discussion. Before we get there, though, I think I still have a question about this one. Yeah, on this one, x squared plus 12x plus 35, when you factor that, what are the 2, when you play that sum and product game, what are in fact the 2 numbers that give us plus 7 and plus 5? Yeah, x plus 7, x plus 5, because that's a pair that multiplies together to give me 35, and which adds together to give me positive 12. And so since one of the factors there is x plus 5, yeah, I'd say that one qualifies as a D. Okay, so that's the only change that I would make to the other ones that are written up here, with the exception now of these last 2. Okay. So for these last 2, it turns out that the sum and the product game is not enough by itself to get us where we need to be. So let's take a look just at just the one on the right here. We're going to factor 5x squared plus 20x plus 15. Let me write that on a separate part of the board here. And so my first question is, what did you do to try and factor this expression? Because you came up with an answer here that you thought that none of the factors in this list were actually factors, so 5x squared plus 20x plus 15. So how did you approach this factoring problem? Before we can use the sum and the product game on a polynomial expression like this one, let's return back to what the sum and the product game first looked like when we were first talking about it last week. The idea behind the game is that we want to undo the process of this lattice multiplication, in which we would take these 3 terms, the 5x squared, the 20x, and the 15, and try to distribute them inside of this multiplication lattice in a way that's going to allow us to work from the inside out. And the way that we usually do that is we take the quadratic term and we put it in one of the squares. We take the constant term and we put it in one of the other squares. And then we start the game of trying to figure out, all right, what numbers can I put here that are going to multiply together to give me 15? But then at that point, we might already have lost the game, because we're also going to be thinking about, how do I break apart a 5x squared? It's no longer as simple as having an x and an x, as it used to be last week. Because we would have to, in some way, account for this 5, this coefficient of 5 that's sitting out in the front. And so one way of approaching that would be to still just play the sum of the product game and just tack on a 5 in here. The problem is that now when I start playing the game of, all right, I need to break a 15 apart into a pair of numbers which multiply together to give me 15, the difference is now saying that they need to add together to give me 20 is no longer going to be accurate. Because when I multiply in this row by whatever this number is, that's not just multiplying an x now, it's going to be multiplying a 5x. And so it's not that we're going to need these two numbers to add together to give me 15, but instead we're going to need one of them added to 5 times the other one to equal 20. And that's a much more challenging thing to think about and try guessing and checking about. You could certainly do it. But this, to me, is not the best way to begin approaching this. A better way is what Arcellus said, which is, let's first, before we even think about the sum and the product game, let's rewind the tape here. And let's first ask, can we use the very first factoring strategy we learned about this semester to cut our problem down to size a little bit? In other words, can we look for and factor out a greatest common factor, a GCF? If we can do that first, it'll cut our complicated problem down to size a little bit more, and it'll let us focus our factoring energy on what's really interesting and what's really important. And in this example, between the three terms 5x squared, 20x, and 15, we ask, do those three terms share anything? Do they share a factor that all three of them have in common? And the answer was, yeah. What do all these three terms have in common? They all have a 5 in common. So before we worry about playing a sum and a product game, let's factor out the 5 from all three of these terms, and then we can come back to the table and think about whether sum and product is an appropriate strategy. So we'll start by, I'm just going to draw a factoring grid around this quadratic, like that, and split these terms apart. And then we decided what we wanted to do was factor a 5 out of all these terms. And if I factor a 5 out of a 5x squared, I'm going to be left with just x squared. If I factor a 5 out of 20x, what's my cofactor there? 4x. And if I factor a 5 out of the 15, I get a 3. Right. So after my first step of just thinking about looking for and bringing out the greatest common factor, I've now turned my original problem into one that's a little bit more tractable. Now, if I'm going to play the sum and the product game, I'm going to play it not on the original polynomial, but now on the simpler one, x squared plus 4x plus 3. And when I play the sum and the product game on that polynomial, how does it factor? X plus 1, x plus 3. Because we needed a pair of numbers there that multiply together to give me 3, and which also add together to give me 4. So now we win the sum and product game, and we had to use 2 steps to factor this particular quadratic trinomial. And looking back in the list of possible factors, yeah, none of the possible factors from our list are actually represented here. We have plus 1, plus 3, and so none of the above was the correctly written answer from up there. But the point of this example was that bringing that greatest common factor out first, that should be a first order consideration. Any factoring problem that you attack, the first question to ask is not to be thinking about sums and products, but first to look for greatest common factors. If you can bring out a greatest common factor and make a complicated problem more simple, then you can focus your sum and product and your other strategies that you use where they're most effective, which is on a quadratic trinomial like this one. And the sum and the product game alone worked on this example because in our factoring grid, we knew how to factor the x squared. There's only one way to factor that x squared in our factoring lattice over here. The only way to do it is to bring it out as x times an x. So we can play the sum of the product game directly as long as the leading coefficient is equal to 1. Remember, the leading coefficient is what we call the coefficient of the highest order term, which in a quadratic trinomial will always be the x squared term. So as long as there is no non-trivial coefficient in front of that x squared, as long as it's just x squared and not 2x squared or 6x squared or negative 12x squared, as long as there's just an implicit 1 here, then the sum and the product game is something we can directly reach for to get us where we're going. Because there's only one way to factor an x squared that doesn't have a coefficient in front of it. It has to be an x times an x. So the next step, where we want to go with this next, is to figure out, well, what if not? What if after doing this process of factoring out the greatest common factor, what if there's no way to account for all of the coefficient in front of the x squared? We still have something here besides 1. How do we handle that? How do we factor a quadratic trinomial with a non-trivial leading coefficient?